Everything around us is in a constant state of flux. Think about your day. The temperature outside changes. Cool morning, warm afternoon. Your height has changed since you were a baby. It might even change a tiny bit during the day. A car driving down the street is changing its position every single second. This idea of change is one of the most fundamental concepts in our world. We see it, we feel it, we experience it from moment to moment. It is the difference between what is happening now and what was happening a little while ago. Understanding change is not just interesting, it is also incredibly useful for making sense of the world. To talk about change in a more precise way, we often ask, how fast is something changing? Is the car moving slowly or quickly? Is the plant growing at a steady pace or suddenly sprouting up? Is the sun setting rapidly or does it seem to hang in the sky? This question of how fast is the key that unlocks a very powerful area of mathematics. It moves us from simply noticing differences to measuring the rate at which they occur. This measurement gives us the ability to predict, to analyze, to understand. These dynamics appear everywhere: the economy, the weather. In mathematics, we have a special tool to measure how fast things change at a single exact moment. This incredible tool is called the derivative. It might sound complicated or intimidating, but the idea is simple and intuitive. The derivative finds the rate of change at one specific instant in time. It's like a magical speedometer. Not your speed over a whole hour, but your precise speed at the exact moment you look. Let's begin with a very simple idea that you are already familiar with: the average rate of change. This is something we calculate all the time, even if we don't use these exact words. For example, if you go on a road trip and you travel a total of 200 kilometers, in 4 hours you can easily figure out your average speed. You simply take the total distance you traveled and divide it by the total time it took. In this case, 200 kilometers divided by 4 hours gives you an average speed of 50 kilometers per hour. This single number summarizes your entire journey. This calculation gives you an average because it doesn't tell you your speed at any specific moment during the trip. You probably didn't drive at exactly 50 kilometers per hour for the entire 4 hours. Sometimes you might have been going faster on an open highway, maybe at 70 kilometers per hour. At other times, you might have been stuck in traffic moving at only 10 kilometers per hour, or even stopped completely. The average rate of change smooths out all of these variations and gives you a single representative number for the whole interval of time. It is a good starting point for understanding motion and change. We can generalize this idea beyond just speed. The average rate of change is always a calculation of how much something has changed divided by the time it took for that change to happen. Think about a plant growing in your garden. If you measure its height today, and it is 10 centimeters tall, and then you measure it again in 5 days, and it is 15 centimeters tall, you can calculate the average rate of its growth. The change in height is 15 minus 10, which is 5 centimeters. The time interval is 5 days. So the average growth rate is 5 centimeters divided by 5 days, which equals 1 centimeter per day. This concept of dividing the total change in one quantity by the total change in another is the foundation for everything we will discuss. It is the simplest way to quantify change over an interval. The formula is always the same. You take the change in the output, like distance change in the output, like height, and divide it by the change in the input, like time. This ratio gives us a slope, which tells us how steep the change is on average. Let's stick with our car example and dig a little deeper. It's a perfect illustration of average versus instantaneous change. Imagine you're on that same 4-hour 200-kilometer trip. As we calculated, your average speed was 50 kilometers per hour. Useful for a general sense of the journey. If a friend asked, you might say, "Pretty smooth. We averaged about 50. That summary hides the interesting details. Think about the speedometer inside your car. It does not show your average for the whole trip. It shows your speed at the exact moment you look. Instantaneous speed. You might glance and see 80 kilometers per hour. A few minutes later, in a small town, you see 40 kilometers per hour. At a red light, your speedometer reads 0. The number is constantly changing, showing speed at each instant. The derivative is the mathematical version of this speedometer. Let's move away from speed for a moment and think about a different kind of change, the steepness of a hill. Imagine you are looking at a graph that shows the profile of a rolling landscape. The steepness of the path is changing continuously as you walk. We can use our idea of average rate of change here as well. At your starting point, you are at a distance of 1 kilometer and an elevation of 50 meters. Later, at 3 kilometers, your elevation is 110 meters. We can calculate the average slope. Change in distance is 3 minus 1, 2 kilometers. Change in elevation is 110 minus 50, 60 meters. The average slope is 60 meters divided by 2 kilometers, which is 30 meters per kilometer. This represents the average steepness over that stretch. However, this average doesn't tell the whole story. The question the derivative asks is, what is the exact steepness at a single specific point? To answer this, we can't use 2 points that are far apart. We need to zoom in. As the second point moves closer to the first, the second line pivots toward a limiting position. So, how do we find the steepness at a single point on our curvy hill? Well, the mathematical solution is, both elegant and intuitive. We start by calculating the average slope between 2 points. The line that connects these 2 points is called a secant line. Now, imagine we keep one of our points fixed. This is the point where we want the instantaneous steepness. Then we take our second point and slide it closer and closer along the curve. As it gets closer, the secant line connecting them starts to pivot and change angle. As the second point gets almost touching the first, the secant line settles into a final limiting position. This final line, barely touching the curve at our point of interest, is called the tangent line. The slope of this tangent line is the slope of the curve at that single point. It represents the instantaneous rate of change. We find the instantaneous rate of change by looking at the average rate of change over an infinitesimally small interval. We can't calculate a slope using just 1 point. That would divide by 0. But we can see what happens as the interval shrinks towards 0. The secant slope approaches a specific value, the slope of the tangent line. This limiting value is the derivative. Back to our car example. To find the instantaneous speed at exactly 2 o'clock p.m., calculate the average speed between 2 o'clock p.m. and 2:01 p.m. That's a good approximation. For an even better one, calculate the average speed between 2 o'clock and 0 seconds p.m. and 2 o'clock and 1 second p.m. Shrink that interval, millisecond, microsecond, and beyond, and the average speed approaches the true instantaneous speed your speedometer would show at exactly 2 o'clock p.m. Now that we have the intuitive idea of a tangent line, we can state the definition of the derivative in a slightly more formal, but still simple way. This formal idea is called the limit definition of the derivative. It captures the entire process we just described with the sliding point. It sounds technical, but it is just a precise recipe for what we have been discussing. The definition is a single sentence that packs a lot of meaning, so we will unpack it carefully. It is the heart of differential calculus and the engine that makes it all work. Here is the idea in one plain sentence. The derivative of a function at a certain point is the limit of the average rate of change as the interval over which you are averaging shrinks to 0. Let's break that down. The derivative of a function at a certain point is what we want to find. Instantaneous rate of change, the slope of the tangent line. The average rate of change is our familiar calculation. Change in the output divided by the change in the input, which gives us the slope of a secant line between 2 points. The key phrase here is the limit. We look at what value the secant slope approaches as the distance between points gets smaller and smaller, approaching 0 without ever actually being 0. This sidesteps dividing by 0 by never setting the interval to 0. We just watch the trend. The value it approaches is the limit, and that limit is the derivative. Calculating the derivative from the limit definition every single time can be a lot of work. It is like building a car from scratch every time you want to drive. Fortunately, Mathematicians have used the limit definition to discover patterns and create simple shortcuts or rules for finding derivatives of common functions. Once you learn these rules, finding derivatives becomes much faster and easier. Let's look at 3 of the most basic and useful rules: constant rule, power rule, sum rule. These form the foundation of our derivative finding toolkit, and they handle a wide variety of simple functions we encounter. First, we have the constant rule. This one is the simplest of all. A constant function is just a flat horizontal line on a graph, like y equals 5. Since the line is flat, its height never changes. It has no steepness. Therefore, its slope is always 0, everywhere. The derivative of any constant number is always 0. For fx7, the derivative is simply 0. Next is the very powerful power rule. This rule tells us how to find the derivative of functions that look like x raised to a power, such as x squared, x cubed, x to the 4th. The rule is, bring the exponent down as a multiplier, then reduce the exponent by 1. For example, the derivative of x cubed is 3x squared. In general, dou dx x yupen n, wow n, x, ao is undita 1. Finally, we have the sum rule. For a function like f(x), wow so 2 pop t5, take derivatives of each piece and add the results. Using the power rule, derivative of x2 is 2x. Constant rule says derivative of 5 is 0, sum gives 2x. Now let's find the derivative of fx boss 4x3 plus an x2. 4x3 becomes 12x2, 7x becomes 7, 2 becomes 0, so fx os 12x2 plus 7. In our discussion today, we journeyed from the everyday idea of change to the powerful mathematical tool of the derivative. We saw that the derivative is simply a way to measure the rate of change at a single, precise instant, like a car's speedometer, the steepness of a hill at one specific spot. We learned that this is achieved by finding the slope of the tangent line. That's the limit of the slopes of secant lines over ever-shrinking intervals.